All right. So, first of all, thank you for coming to this session early in the morning. Do you have enough coffee? You have enough coffee? Because we're going to do some real brainy stuff. Okay, we're going to try to understand large language model, agents, and all that. Okay? So, all right. So without further ado, let's get started. So I'm sure all of you have seen the power of large language models such as ChatGPT, right? You know that it can generate text, images, audios, and video. You all have probably tried it, or your kids have tried it and show you some amazing thing they're able to do with it. Now the question is, well, what does this have to do with airline revenue? What does all this have to do with anything to do with airline revenue generation, right? Can ChatGPT generate revenue? Can it? Right? I mean, you can generate a lot of stuff. It's called generative AI, right? Can it generate revenue? Well, let's see how, okay? Let's see how we could do it, okay? So now to understand that, we really have to dive a little bit deeper to understand how these large language models work and how these large reasoning models work and how agents actually work, okay? Now, so I think the best way to understand this is to kind of follow OpenAI's kind of model for their development of GenAI. Basically, this is a 5-stage model, right? It starts with, the ChatGPT, the chatbot that we all are very familiar with, okay? And then, you all know that chatbots are great for certain things. They're great for writing poems, writing your emails and everything. But if you ask them anything that it doesn't know, what will happen? You hallucinate, right? You make things up. Right? So that's terrible, right? So, and if you ask it to solve some problem or write some code, it's not going to be able to do it because it's going to make things up, right? So the next stage of that evolution is basically OpenAI come up with a series of these old models. So the O1, O3, and now, this old series of models are much more powerful. They are what we call the large reasoning model. So they're able to, even though they're completely different model, you actually use them just the same way. Now, use them just as you would use, the chatbot, the large ChatGPT, and so on, right? But behind it actually works very, very differently, okay? So now they can actually solve problems because they could reason, they could think, okay? And then comes to agents, right? So 2025 is known as the year of agents, so we're going to talk a little more about that. And then basically, once you get to agent, right, you can take actions. Now you can actually start to innovate and basically improve yourself. The AI, when AI is able to improve itself, what's going to happen? You're going to get AI that gets smarter and smarter and smarter and smarter exponentially, right? And that's how you get to artificial general intelligence, right? That's essentially AI that has human-level intelligence, right? Okay, so that's the evolution of how OpenAI proposes the development of Gen AI. So let's see how this applies to the airline industry. But before that, let's try to review a little bit about how these chatbot large language model actually work, okay? So you probably know by now that, large language models simply try to predict the next word, given some kind of prompt, right? So they do that by essentially modeling this probability distribution here, probability of the next word given a sequence. And that sequence initially is given by the user as a prompt, right? You give it a prompt, and then you basically predict the next word, and it give you the sentences and the paragraph and the entire response, right? So basically, it does that, iteratively through this kind of feedback mechanism, right? Basically, once you have the prompt, right, it samples the next word, right? And that next word gets concatenated into your sequence. So your sequence becomes one token, one word longer, and then you feed that sequence back to that probability distribution again, so you sample the next word, okay? So that's basically how they generate your entire response. It does this by this recursive generation loop, all right? Okay, now, we also know that because this probability distribution of the words given the sequence is actually not zero anywhere, that means you can actually generate content that didn't exist before. It never existed. Completely novel content is able to generate that, okay? So when I said, probability is equal to 0, that means it actually has never existed in the training data. Yet, it's able to generate that, okay? Because this probability here is actually not 0, never 0 anywhere, okay? Now, how do you make it generate new stuff? You prompt it, right? You simply prompt it, right? And so if I give you a very simple prompt, right? The date is, So what's the next word? What would you guess the next word is? Day is today, right? Good, right? So it could be many things, right? So you say, but day actually is a very interesting example because day actually has many different connotations, right? It could be a calendar day. It could be the fruit, right? Day is actually a fruit, right? In the Middle East, it's very popular. It could be a romantic day as well, right? Gathering between individuals, right? So depending on what your context is, so next word could be very, very different, right? And all that, just means that like there are lots and lots of possibility for the next word. Right? That means that it has a wide spread. The response is very uncertain. Okay, so if you look at this distribution P of W given S, right? This distribution right here, empirically, this is what it actually looks like. And let's take a look at what is the probability of the word metallic. Basically, this metallic almost had nothing to do with any of these connotations of date, right? Basically, if you look at the word metallic here, the probability will be exactly 0. If you look at the training data, no one will ever say the date is metallic, right? Under whatever connotation you may have, right? Right? It's kind of, that doesn't make any sense, right? So now, so here's what the idea that I want you to have, right? So this is empirical distribution. Empirical just means that it's actually obtained from data. From real data, okay? So this, just as a sample here, right? This is actually the empirical Gaussian distribution. You get that from actual data, okay? But that doesn't mean that's the real Gaussian looks like that. The real Gaussian is a smoothed out version of that, right? And the difference, so this empirical Gaussian distribution and the true Gaussian distribution looks very similar, but there's some really, really important difference. The main difference that's really, really crucial is that like, out here in the tail, right? The empirical Gaussian distribution have some areas where you have 0 probability, right? This blue is actually 0 probability. This is absolutely 0, okay? It's not just small numbers, it's 0, right? Whereas this pink distribution here is not 0. It's not 0, okay? That means there is a possibility that those words could be sampled, right? Because it's not 0, right? But if you look at the empirical, it's actually exactly 0. Just as this one, right? Metallic, if you actually look at the empirical probability, it's actually exactly 0. You never see people say that word, right? Okay. So now how would you prompt it in a way to make it say the fruit, so the date is metallic? You prompt it. You add a prompt, right? You say, the fruits in Fruitopias are made of gold, right? The date is metallic. Now it also makes perfect sense to say it's metallic, right? So now what happened? When you actually give it a little more context, right? Like this, right? The fruits in Fruitopias are made of gold, so the date is metallic, looks like this, right? So what are you doing here? What you're doing is that like you give it a longer prompt that has more detail, right? So for example, you talk, given this prompt, this longer prompt, right? You're talking about the connotation of fruit. Right? You're not talking about the calendar day. You're not talking about romantic day. You're talking about fruits. Right? So you narrow down your possibility. Right? Eliminates a lot of possibility. Right? So what that means is the probability distribution sharpens. The response is actually a lot more certain. Right? When the probability distribution is sharpened, right? It concentrates. It means your response is actually a lot more certain. Okay? Just as if you look at a Gaussian distribution that's very, very wide, the response could be very uncertain. It could be any of those numbers. Right? But if it's very, very sharp like this, then it's actually very precise, okay? It's more precise. It's not going to be exactly very precise, like, because you're not going to get a delta function, right? So, okay, so what that does is that like when you prompt it this way, the fruits in Fruitopias are made of gold, right? You redirect the model's attention to focus on words that are related to gold, okay? Words that are related to gold, right? For example, what are those words? Those are, for example, these words, right? And what are these words? These words get actually, what happened to these words is that they get multiplied by a big attention factor, because now now your mind is focused on something that's related to goal, right? So you basically any word that's related to goal, you give it a big multiplicative factor. They get multiplied by a big number. That's all. Okay. So these words are, for example, these words, right? Golden, shiny, metallic. All these words are related to gold, right? So they get a big boost of probability. Okay. So now all of a sudden, what you know is that like, the longer and more detailed prompts give you more precise and accurate response. And, by creative prompting things, right, you can actually get a novel response, right? Even though you never, ever, ever hear people say the date is metallic, right? You could prompt it in a certain way to make it say so, okay? By just creativity, right? Okay, so yeah, so now, when you say, the fruits in Fruitopia is made of gold, the dates it's actually very likely that you could say it's metallic, okay? So, so there's another concept I want to talk about is temperature, okay? Temperature just controls how creative your language model is, right? Basically, this is the effective range of token that you sample, right? So when you have temperatures non-zero, you will sample from a Y region, from this probability distribution, okay? You will sample this word, all these words probably all the way out here. But if your temperature is set to 0, it will only sample the most likely word, okay? It basically removes this indeterminism. There's not completely, but there's something that the language model actually does that's called batching, all this stuff, right? But technical detail that you don't need to worry about, okay? So, okay, so that's how we know, that's what we know about how large language models work. So let's move on to the next stage and see how these large reasoning models work, okay? So we all know that reasoning is actually fundamental to problem solving. That's why these large reasoning models, they're also called problem solvers. Okay, they're problem solver, right? So reasoning is fundamental, and there's something called the chain of thought prompting, okay? And they actually improve the large language model's performance significantly, okay? All of a sudden, they become PhD level smart, smarter than like probably any one of us here, okay? Or in fact, all of us combined here probably, okay? So crazy smart, okay? So yeah, so what is this chain of thought prompting? So let's take a look at one example, okay? There's one example. I want you to think about this, okay? If I give you the prompt, the farmer has 10 sheep, all but 3 run away, so he got 2 more. How many sheep does he have now? What's the answer? Come on, you guys know how to do arithmetic, right? Huh? Okay, yeah, okay. So, good. But sometimes, okay, the language model will say, 9 sheep. 9, right? That's ridiculous. That's ridiculous, right? Why would it say 9 sheep? Right? If you actually look at it, if you think about how the large language model work, right? You know that's incorrect, right? That's incorrect. You know that's incorrect, right? But let's try to understand why it's incorrect. The reason is because if you look at this prompt right here, right? If you simply remove one word, that word all right there, right? A farmer has 10 sheep, but 3 ran away, right? So you got 2 more. How many does he have now? Then 9 will be correct, right? Okay? You see? So now you really have to see, this is actually illustrate this properties of the large language model perfectly, right? It actually doesn't understand what you said, right? It's just trying to predict the next word, the next token, the next word. That's it, right? So if you have this prompt without this all, without this word, right? Then the next word, 9, and next word, sheep, would be correct, right? But if you added this one word in there, right, then sometimes it actually did not it actually doesn't know that this actually the grammatical construct of that word. It doesn't actually know what it actually means, right? It's just trying to predict the next word, and sometimes that will actually give you the 9 sheep. Okay, so now what is chain of thought? Chain of thought improve your performance of your large language model by asking this language model to essentially think step by step, right? You give it whatever prompt that you have originally that you have, exactly what it is, okay? And you just ask it to please think step by step. If you ask it to think step by step, it will actually give you all this response, all this thinking, right, going on, right? It basically says like the farmer starts with 10 sheep. The phrase all but 3, means that 3 sheep did not run away, okay? All but 3 means 3 sheep did not run away, right? Then you got 2 more now. It's got, so you got 5. So now the answer will be correct, okay? So this is the thinking step that's going on, right? So this very, very simple prompt requires this large reasoning model to think through 4 steps of thinking, okay? 4 steps. Now, the interesting thing that you should start to wonder is like, why this like chain of thought will improve the performance of a language model? Why would it improve it at all, right? Because you're not augmenting this model in any way, right? You're not enhancing the knowledge in any way. You're not giving any document to read or any, you're not retraining it, right? You're not doing any retrieval augmented generation. Why would just asking to think step by step improve the performance significantly? Why? Okay, that should be something very curious. If you know anything about machine learning, This is unusual. This is very, very unnatural, okay? Now, but if you actually think back about what we know about how large language models work, it's actually very, very simple, right? So large language model works by this recursive generation loop, right? I told you this before. But we also know from the large language model that a longer and more detailed prompt give you a more precise answer, right? Remember, the probability distribution sharpens, right? If you give it more context, it eliminates much more possibility, so the probability distribution sharpens. When you do that, the answer becomes much more precise, much more accurate, right? Okay, so if you understand that, then the next step is really easy, right? Chain of thought must generate a lot more token to explain what it's actually thinking, right? You have to generate all those words, all those tokens to explain how you actually all think through all the step by step. But remember, every word that it generates, right, goes back into this probability distribution before you can sample the next word. Okay? See what's going on? So basically, the effect of chain of thought is exactly like as if you write out a very, very long and detailed prompt. Except you don't have to write it. It's generating all that for you, right? It's generating all that for you. It's as if you write out, all but 3 means like 3 did not run away, all those explanations, as if you write it all out yourself. But you don't have to write it. It's doing that for you. It's generating all that for you. Okay, that's chain of thought, okay? All right, so now chain of thought is really curious, okay? So now in many of the real world problems that are, any substantial difficulty, right? It may require tens of steps for you to actually reason to the answer. Right? If you talk about some of these really challenging scientific problems, for example, in revenue management, a lot of times they're very, very difficult, right? So may require hundreds of steps of reasoning, right? And that's actually very difficult, right? So now let's just imagine each step of your chain of thought reasoning is 99% accurate. 99% accurate. What happens after 20 steps? Your accuracy basically degrades to like 81%, right? After 50 step, it's barely above 60%. After 100 step, forget it. Your chain of thought is no longer answering your question that you originally asked anymore. Okay? So what that means is that, deep reasoning, this very, very deep, long chain of thought, right? Many, many steps, multi-step reasoning, requires your large language model, to be almost 100% accurate. Right? Otherwise, this compounding effect, right? Just raise it to any power. If you take anything like 99.9999, right, raise it to like 100, or you're going to get some really small number, okay? Because it's compounding effect. The error actually compounds, okay? So how do you get a large language model that's almost 100% correct? That's really, really difficult because large language model hallucinates, right? So how do you get it to be nearly 100% accurate? Okay, so let's think about this a little bit. How do you improve the performance of a large language model? Well, we know the large language model is the statistical probabilistic model, right? It's basically trying to model this probability distribution, probability of the next word given the sequence. And you do that by training, right? Sometimes that's called pre-training or fitting the model and so on, right? Okay? And after you train that model, right, when you actually use that model, it's called inference. Right? Sometimes that's called test time, scoring, or all that stuff, right? So that's inference. So the thing to keep in mind is that when you actually using the model, right? When you're actually using it in a live situation, like in ChatGPT, you're talking to it, right? You're no longer changing the model parameters. So all this model here, this probability of W given S, it's a probabilistic model, right? So it has free parameter. When you actually are training it, you're trying to determine the value of those free parameters, okay? So if you know anything about machine learning, how do you improve the model? What can you do to improve the performance of a model? When you are training it, what can you do? Well, there's a few things you could do, right? You could train it with more data, right? You could train a bigger and more complicated, more complex model. And you could even use more compute time to train it for longer, right? So if you actually do train it with more data, right? Basically, the error actually drops. You can see that right here. If you train it with more and more token, right? This is the test error. The error drops. When the error drops, it means your accuracy increases, right? Same thing for a model. If you train it with a bigger and bigger model, right, more and more parameters, right, then error drops and your accuracy increases. Likewise for compute time, okay? But it turns out that these three, so what that means is that like an exponential increase in training resources, right, give you a linear increment in accuracy, right? So if I want the model to perform 10% better, I would need 10 times the data. If I wanted 20% better, how much more data do you need? 100 times the data. And you need to train a model that's 100 times bigger, and you have to train it 100 times longer, okay? If you wanted 30% more accuracy, right, what do you need to do? You need 1,000 times more data. You need to train a model that's 1,000 times bigger, and then train 1,000 times longer, okay? So the thing to recognize is that these three components are linked, okay? So you cannot scale up one component without the other, right? If you scale any one or any two of them up without the other one, the one that you did not scale up becomes your limiting factor, okay? So it won't get any better if you actually scale them up, okay? So now, this scaling law is actually what kept OpenAI running for the past 10 years. Actually, OpenAI has been 10 years, okay? 2015, okay? So, yeah, so what they did is that they simply trained the model with bigger and bigger model, you know, using more and more data, and train it for longer and longer, okay? And their model just keep getting better and better, okay? The problem that they run into today is like, you know, they're running out of publicly accessible data. Every possible data that the OpenAI could ever use to train the model, they have used. There's no more publicly accessible data out there that they have not used, okay? So what does that mean? That means you're stuck, right? You can't get any better, right? Because remember, these components are linked, right? You could train it longer, and you could train a bigger and bigger model, right? But because you don't have enough data out there, so that becomes a limiting factor, so you just can't perform any better. That becomes your limiting factor, okay? So that basically, what can you do on the training side to improve the performance of your model on the training side? There's pretty much nothing you can do in terms of, you know, training, right? But what about, you know, inference? What about inference? Anybody know what this thing is? No? It's a quantum computer, okay? All right, we're not going to use quantum computers to solve the problem, right? Quantum computer is not the answer to everything, okay? But we borrow an idea from quantum computing. Is that we use to use statistics to solve the problem, okay? So what that means simply is that, like, you know, if you ask, you know, the OpenAI's ChatGPT, right, the same question 1,000 times, right? Just we parallel generate a lot of these answers. Ask the same question 1,000 times. And, well, sometimes you're going to get different answers, right? Because remember, ChatGPT, you know, have you ever tried to ask the same question to ChatGPT, you know, over and over again? You may give you a very, very different answer from one time to the next time, right? So now you can actually look at all those 1,000 answers and pick the best one, right? So that will improve, right? If you generate 1,000 times, right, you could actually give you a slightly better answer if you select the best one out of the 1,000, right? Certainly better than if you generate the first time, right? So that's called parallel generation. There's actually many ways, you know, to generate these parallel generation. You know, all those involve like generating, increasing the temperature. Remember I told you about the temperature parameter to control how creative this language model is, right? If you increase the temperature, this language model is going to be really, really creative. Right? If you ask them the same question, it may give you a wildly different answer if you increase the temperature up, right? So if you crank up the temperature, right, generate lots and lots of answer, then you can actually see which one is the best one. So the question is, how do you determine what's the best answer? Well, there's also many ways to do that, right? How do you pick the best answer? You can have a human to be the judge, right? Of course, that won't scale. Or you can have a model, some kind of reward function, right? Some other model to determine how good this model is, right? Or you can have a verifier. Now, verifier is really interesting. Verifier is something where you actually know what the true answer is, right? For example, when you ask the large language model or these reasoning model a math problem or a coding problem, right? There is an actual precise answer. There is an answer, right? Right? How would you know how would you know what the answer is? You give it to a compiler. If you're asking a coding problem, you can give it to the compiler, see if it actually compiles. Right? If it compiles and the code actually does what you tell it to do, then it's a good answer, right? So you know, so those are essentially for problems where we know there is actually a precise answer, you could use a verifier, like a compiler or something, right? Or a math engine or something like that, okay? Or you could use even another language model to be the judge, right? Okay? So if you're using another language model to be the judge, basically you could do what we call sequential refinement, right? You could generate an answer, okay? And then ask the language model to critique itself, right? Okay? And then basically you take the critique and ask it, based on this critique, can you generate another answer that's better, right? And you do this over and over again. So sequentially it's going to get a better and better answer, right? Okay? So all of these, whether you do it in parallel generation or sequential refinement, these are what we call the thinking behavior. When it's actually doing all that, it's actually thinking. It's actually thinking, okay? So now, thinking actually requires a lot of memory, right? Whether you are doing it in parallel generation or sequential refinement, it requires a lot of memory, right? Because, if you generate like a million answer, right? How do you know which one is the best? You have to remember all a million of them, right? To essentially figure out which one's the best one, right? If you forgot the first 100, right? What if the best one is within those 100 ones that you forgot? Right? You have to remember all of them. Likewise, if you do it in sequential refinement, you also have to remember all the steps along the way, right? What you don't want happening is okay, I generate an answer, like the 2057 iterations of refinement, it basically went back to the fifth one, right? They just go in circle, right? So you have to know that, you have to make sure that the language model remember everything before, so it doesn't actually go back and generate something that's like the one that you have before, right? So you actually generate something that's different from every one of the one before, right? So it needs a lot of memory, okay? So now if you actually give it the memory, but essentially the context length of this language model getting bigger and bigger, right? Then they perform amazingly, okay? They are basically almost like scary, okay? We give these language model, there's no longer the language model that we're familiar with anymore. That's why they call the reasoning model, large reasoning model, right? We basically give them like competition level math problem, give it competition level coding problem, ask them like PhD level science questions, right? Okay, so if you actually look at the performance, right, in competition math, right, if you look at the GPT like 4, right, so these are the non-thinking model. These are the regular chatbot, okay? The non-thinking model, they basically fail, right? 13%, 11%. I mean, they do decently well if you ask them PhD level questions, 60%, okay? But keep in mind, these language models, they have read every single book out there, every single published journal paper out there, right? So they could certainly answer those questions, no problem, okay? But now what happens if you let it think, right? So remember, the GPT, 3.5, 4, 4.0, right? These are the non-thinking model. The 01, 03, 04, those are the thinking model, right? If you give it the 01 model, right, all of a sudden their performance jump up like to 50%, 60%, right? Okay, and in the science question, right, they basically gotten up to almost 80%. Now the scary thing is like from failing here to spectacularly passing it, right? And the thing that I want you to draw your attention to, right? Even human experts can only do like 70% of these tests, okay? And these models are beating human experts, human PhD level, professor level experts, okay? So, right? And that's scary, right? That's scary, right? So now if you actually look at the performance of these computing time, if you train it for longer and longer, right? In training time, it actually increases, but it actually eventually plateaus off. But if you actually do this test time compute, right, at inference time, just simply let it think longer and longer. Instead of generating 1,000 answers, let it generate 10,000, 100,000, a million, 10 million, 100 million of answers, right? And then pick the best one, right? We are not seeing any plateauing so far, okay? So far. We think it will plateau, but we have not seen it yet, okay? So what that means is that, if you continue to scale up this test time compute, right, basically you will continually get improved performance, right? That's crazy, okay? That's crazy. So this is actually sometimes we call the most important discovery in AI for the last, I would say, several decades. Okay? The most important discovery in the entire field of AI for the last 3 or 4 decades, 30, 40 years. Okay? It's this test time compute. Basically, there's a new way to improve the performance of this language model. It's simply let it think longer. Simply let it think longer, okay? And the beauty of that is that all you need is compute, right? What does it take to let them think longer? You don't need more data. You're not training, you're not retraining it, right? And you don't need a bigger model. You're using the same model, right? You simply let it think longer. All you need is compute. All you need is compute, right? Whether think about this. What does it take to do parallel generation? Instead of generating like a million, give it like, 100 million or billion answer. You just need more compute, right? Same thing. If you do sequential refinement, what does it take to do 1,000 or 10,000 times the refinement? Just more compute, right? And that's actually why trillions of dollars are basically poured into quantum computing and fusion energy and all that stuff, okay? It's amazing. So now, everyone have essentially access to essentially a PhD level problem solver. All of us have access to this PhD level problem solver today, okay? So let's put it to work, okay? So recently I actually moved into a small apartment. I'm transitioning between homes right now, okay? Almost like a homeless in San Francisco, right? Transitioning between. So I need a very simple desk, right? So I took advantage of the multimodality feature of this large language model, and I saw this desk that I kind of like, and I said, this looks like a simple desk that I could build myself. Let's just ask ChatGPT how will you build it, okay? So I take a picture of this, right? And then give it to ChatGPT. That is really me there, okay? So how do you build this table? It will tell you in great detail all the tools and materials that you needed and all the steps that you need to follow to actually build this table. Everything from cutting to assembling to painting it to where you put it to enjoy it, okay? But at the end, you still don't have a table, right? You don't have a table. Why? Because it can't take any of those actions. It could tell you what to do, but you cannot take those actions for you. Okay? That's why. And this is actually why we need agents. Okay? That's why we need agents. So agents, I'm sure all of you have seen the movie Matrix, right? You all know this guy, right? Remember this guy? Agent Smith, okay? So, if you remember, the movie Matrix is actually inspired by real-world concepts in software agent. Now, these agents in the Matrix, right, they actually have a lot of characteristics that's actually very true to, I would say, the agents we talk about today, right? So they're certainly goal-directed, right? So they're, for example, Mr. Smith is actually programmed to keep order in the system, in the Matrix, right? And they have autonomy. They could actually decide whatever they want to do, necessary to do, right? They could do whatever they need to do to achieve that goal, right? They would do whatever is necessary, including eliminating rogue programs or humans in that case, right? To keep the matrix stable, right? And they are context aware. They can basically monitor the entire matrix everywhere. They could appear out of nowhere, right? You can see them all of a sudden they just appear out of nowhere in the matrix, right? So that's context awareness. They can monitor everything and basically show up everywhere. And the thing that gives them the superhuman ability is the tool usage. They can basically use anything and anyone, not just anything, but any humans in the matrix, right? They can actually go into somebody's body, right, and take over that body and then basically, be that person, right? So they could use anything in this matrix, right? And that gives them the superhuman power, okay? So now, you may also know that Matrix is a pretty old movie, right? It's back in 1999 when we had this movie. So the question is, what's all the hype about Agent today? What's all the hype about Agent, right? So let's understand why, okay? So if you look at all of these characteristics of agent, right? So they certainly map very closely to the agent that we talk about today, right? So we have goal management, we have autonomy, we have context awareness, and tool usage. That tool usage is actually the hallmark that separates the agent from this large language model and the large reasoning model, okay? Large language model can generate a lot of things. Large reasoning model can even solve a lot of problems, right? But they can only tell you how to solve those problems. You can actually solve those for you, okay? So if you're actually able to use tool, then you can actually potentially solve those problems for you. Okay. So now at the core of these agents, right, basically it's still a large reasoning model. So these are the problem solver, not the chatbot type anymore, okay? They're able to, so what that means is that they have reasoning ability through chain of thought, and they have lots of memory, okay? And you also have this, what we call the action reflection cycle, or the reasoning action cycle, right? So they could, through this chain of thought reasoning, you can actually plan your next step, right? Plan all the steps to achieve the goal, right? And yeah, when you actually plan, you can actually take the action using the tool that you have access to, right? Take the actions, and once you take certain actions, you also need to be context aware, be able to monitor the result, observe the result, right? And once you observe that result, right, you need to reflect. Reflect just means that you have to check against your goal, right? What are you directed to do? If you actually achieve the goal, then you're done, right? And if you did not achieve the goal, what happens? You do reasoning again, right? You do reasoning again, and then you basically plan your next step, and then observe, see if you get closer to the goal, right? You just do that over and over again until you get to the goal, right? So that's in essence how these agents actually work, right? So now I find it somewhat useful to compare these agents compared to just an ordinary program, just to see the difference, right? So ordinary program, right? If I say, I want a table at the end, right? What would you need to do? What does a programmer need to do? The programmer will have to basically program every single execution step, right? To get to the table, right? For example, they would say like, I need to get some wood, I need to measure, I need to cut it, I need to assemble it, right? And there could be like branching conditions, right? If you have, for example, if you have nails and you assemble it with a hammer, if you have nuts and bolts, you assemble it with a kind of wrench and screwdriver, right? And then after you assemble it, you want to paint it, you could paint the big area with a roller, and you paint the smaller area with a brush, and you get a table at the end, right? That's what a programmer would do. That's what an ordinary program would do. You specify exactly what every execution step has to be to get to the goal, right? Okay, so now this is a program, right? A program is written by a user, it's executed by the user, or it could be executed by other program too, because other program can call and execute this program, right? Okay, now let's think about what is the difference. How is that different from a software agent, right? A software agent basically can have some autonomy. They can actually determine when to execute, right? So what that means is that they have to be able to observe the environment to know when is the right time for them to execute themselves, right? When is the right time to self-execute, right? Okay. So now, they're still very task-specific. So they're goal-directed. So these are really, really great for automation, right? So some examples in the early days since the 1999s, right? You've seen like web crawlers, load balancers, right? And also something like Mr. Smith. Agent Smith, okay? So Agent Smith is actually modeled after what we call a network intrusion detection agent. It can monitor the entire network. If it detects an intrusion in the network, it's going to go and terminate that process. Doesn't that sound like what Mr. Smith would do? Right? Agent Smith would just do that, right? So, okay. So now a software agent is basically a program that has autonomy and context aware. That's all it is, okay? Now, what is an LLM agent, the agent that we are all raving about today, okay? An LLM, the large language model agent, is basically, you tell them what goal you want to accomplish. I want a table at the end, but you also tell it what tool and resources it has access to. These are the tools that you can use, and these are the resources that you need to get, okay? Then you don't specify how to get to that goal. Because the large language model, right, the large reasoning model, it already has reasoning ability. It can reason about how to get to the answer, get to the goal that you want, right? So maybe one time you would say, okay, one way to get to the table is like, okay, I may get some wood and paint together, right? And I'll measure it, cut it, assemble it, and paint it and get the table, right? You could get there that way, right? But then if you ask them again, I want a table, it may give you a different answer. It may actually give you something like this, okay? Maybe you can measure the table first, right? To see how much paint and how much wood you need to get, cut them, and then paint them, the big pieces together, and then assemble it, and then touch up the small areas that and you get the table, okay? Or you can say like, give me a really, really simple answer to get to the table, right? Then you may say, okay, if you want a really, really simple answer, right, then maybe you can measure these, really, really precisely and get the wood in precise dimension that you don't even need to cut it, right? Then you can just simply assemble it, paint them, and then you get a table, right? That's it, right? So now, there's no specified execution path anymore. The execution path is determined by the reasoning capability of these agents, right? This language model, okay? So now, one thing to really keep in mind is that like these agents, right? The way they reason about to get to the answer depends on what tool do you give access to it, right? If I give it a new tool, right? If I give it this new tool, say it's like sandpaper right here, okay? And then I say, give me a simple way to get a table, right? Then it will tell you, okay, measure precisely, right? So you get the wood in the exact dimension that you need, assemble them, right? And then you want to sand them before you paint them, right? Before you get some paint and paint them and get a table, right? It would change how you actually get to the answer because now you have a new tool, okay? All right, so basically the large language model must use tool to take action. They have to. Otherwise, it could tell you everything how to do, it could tell you essentially precisely how to perform any task, but then you have to still do all those tasks, right? It cannot actually do any of those tasks for you, okay? So in the digital world, basically these tools are basically other programs, other APIs, or other agents. That's it, okay? So an API, right, you may think there's some kind of software, right? But it doesn't have to be. It could be a robotic, it could be an API that controls a robotic arm, right? Okay? Robots are coming, believe it or not, okay? They are coming, whether you like it or not, right? And how do you control those robotic arms to actually assemble a table? You call an API, okay? It's that simple, right? There's no difference between controlling a robotic arm or executing some software API, okay? Whether it's a robotic or a computer software, okay? So now, so why is agents such a big deal today? And the reason that they're a big deal today is because they are a major milestone toward AGI. And the reason is because previously, before, so the way that OpenAI defines artificial general intelligence is that like basically they do this operational definition. These are AI that has human level performance at most of the economically valuable work. What does that mean? That actually sounds a little scary, okay? That means AGI, right, is an AI that could do all the work that you and I do and get paid for and do it just as well as you and I do it. Okay? That's how they define it. Okay? All right? So now, so if that's a definition, then it makes perfect sense why agents are a major step toward this AGI. Because before you get to agents, right, even you have a PhD level smart large reasoning model, right? It could tell you what to do, but you still have to do all those work, right? When you have agents, you can actually start doing automating those tasks for you. That's the amazing thing, okay? So now the question is like, still coming back to, can these GenAI actually generate revenue, right? And the answer is not by itself, not alone, not by itself, okay? The key thing to recognize is that an agent is only as good as a tool that you have access to. Right? If you have an agent, right, that have access to crappy tools, it's going to do a crappy job in all this automation, right? All right? So now, what kind of tool generates revenue for airline? What kind of tool generates revenue for airline? You all know that, right? Well, we have lots of tools that could generate revenue for airline, right? So basically, if you look at, from everything that in revenue management, right, in getting the offer, the right time to the right customer, through the right channel at the right price, right? All those are tools that we build, okay? And every one of those essentially are some kind of AI, right, behind it. And all those AI has proven that to generate revenue, right? So with continuous pricing, you can actually, with willingness to pay model, right, you can actually improve the revenue 1 to 3% in addition to just using conventional revenue management, right? And if you actually do this request-specific pricing, right, Florian here could tell you the answer, right? So, you could get additional 5% more, okay? And if you actually do this dynamic ancillary pricing, you get 6% revenue lift, okay? So now this one, I want to qualify this a little bit, right? This is actually 6% revenue lift to the ancillary revenue, okay? Not your seat revenue, okay? So this is actually, so don't misquote me, okay? So, all right? So, and then with offer marketing, right, you could get like 192x like ROI, okay? So all these are generating revenue, right? So basically, what you need to do is like turn those into tools that this agent can use, right? Then you tell the agent that, okay, the goal is to maximize total revenue. Then the agent could reason and think of whatever path they decide to execute it, right? And you may even try many, many different ways, right? To get to that goal, okay? So now, question I have for all of you. How many of you here is ready to let agents make all their business decisions fully autonomously here? Not very many people, right? Not very many people here. It is pretty scary, right? Okay? So how do you get there? How do you get to this future world of where agents actually, making most of the decisions, automating most of the work, right? Getting to this AGI, right? So this is the AI automation roadmap. Right? So it basically starts with what we call AI assisted, right? Where the humans are the main driver, right? And the AI is basically an assistant ready to help, right? So AI is a helper, right? Human is the main driver, right? And then we go into what we call the AI led. AI led is basically now the AI become the driver, right? But humans still need to approve all the works, okay? Humans still need to approve all the work. Humans are essentially an approver here, right? And then eventually you have AI automated, right? AI automated, basically AI is still the driver, but now humans don't even need to approve all the work. Basically, they just need to intervene when the AI had trouble, okay? So let's see how this plays out a little bit, okay? How this plays out is that like, in the AI-assisted world, right? Humans still are the main driver. We still do work as we normally would do, right? We still do all the work. And now the agent's actually there suggesting actions for you to take. Suggesting action, okay, you could do this, maybe you could do this, right? Suggesting, or you could just be passive there, listening to what they want to do, right? So basically, it's actually waiting for you to prompt it to do something, right? It's there, with essentially a chat kind of window, a chat bar there for you to talk to it, right? So it's suggesting you stuff and listening to you to see what you want it to do, right? So humans, what do humans do? Basically, you could either do two things, right? You could either approve one of the suggestions that it actually provided, or you could prompt it to do something new completely, right? So when you actually approve or prompt it to do something, then it's going to actually go execute those actions. Remember, these are agents, right? They can actually take action. They have access to tools, right? That's necessary, right? So now, after you finish those actions, basically it's going to generate the report and the exceptions, and all those basically feedback to help the agent improve the suggestion in the future, okay? So that's how in the AI-assisted world works. I think a lot of you probably have seen this already from some of the vendor that you work with and so on, right? The AI is there suggesting things, or AI just passively with the chat window there waiting for you to prompt it to do something, right? Copilot, all those are something like that, all very similar type of workflow. What's AI-led look like? AI-led basically say, okay, AI will suggest how you should work, okay? How you should work. Basically, it's there to essentially analyze your work environment, prioritizing the task for you, right? And then suggesting actions as well. But now, humans have to look at all those kind of suggestions and essentially see what do you approve, what do you not approve, right? If you approve, right? If you approve here, right? If you approve the suggestion, right? Then basically the agent is going to go execute those tasks. What if you don't approve? What if you don't approve? If you don't approve, right? That means you have to go execute those tasks yourself, right? You have to, if you don't, what he suggested is not good for you, then you do it. Right? You do it yourself, right? So humans need to execute the revised task, okay? So, but as you're executing these revised tasks, right? Those tasks, those user behavior, how you actually executing those tasks, get feedback to the agent. Now the agent learns, oh, this is how you do this task in this context, okay? And it learns, okay? So next time, it will suggest the right task for you, right? But you still need to approve it, right? So in this case, right, humans still approve everything. Every single task, right, still approve. So human knows what's going on, right? All right, what's the future look like? basically in the AI automated world, most of the work will be automated, right? So here, the AI will basically monitor the work environment and execute the task whenever the trigger conditions are met. Okay? It doesn't require human to approve anymore, right? Right? When the conditions are met, it's going to execute, right? So now the key thing is you want to actually specify and basically these trigger conditions, right? Maybe at the beginning you want to be very, very stringent, right? You have to be 99.999% confident that this is correct before you execute, right? If it's only 0.001% you're uncertain, then leave it to me, right? Something like that, right? So, but you could actually loosen these type of trigger condition over time, okay? So, okay. So now when basically it's going to execute all those things that is when the trigger conditions are met, right? So all those things that it has done, right? It's going to generate a report with the results and exceptions of what it has done, right? And if there's something that's urgent, then it will notify you, right? Notify and alert the user when there's something urgent that you need user's attention, right? So what does the user do then? The user basically said, okay, you basically intervene at these exceptions, right? So you could do it. So suppose there are some urgent exceptions, then you just come and look at it and see what happened. What would you do? You need to deal with it, right? Suppose there are no urgent exceptions, right? At the end of the week or at the end of the day, right, you get a report of all the results and exceptions. So you say, oh, here's all those exceptions, right? And you deal with it at the time, right? So that's all these, feedback of the user behavior essentially goes back to teach the AI how to essentially, do the work in the next round, okay? So that's how this AI automation roadmap happens. This is what people mean when they say going from AI assisted to AI led to AI automated, okay? So you can see that the role of the human and AI almost reverse, right? So here, human start the work and can work continuously, and basically the AI is just intermittently helping to complete the task that's needed. Whereas here, AI actually start the work, right, and working continuously, and humans are intermittently intervening as to help AI complete the work when they actually can do it. Okay, so we actually have some examples of PROS agent that actually help you do that, right? So for example, we have these AI-assisted kind of merchandising bundling agent, right? You can ask it to suggest some kind of suggest a bundle, right? It can actually help it price it, right? And even actually create a bundle, right? So all those are things that you can actually ask it to do, right, for you. And we also have something kind of almost to AI-led, okay? So this is, it's actually looking at your work queue and actually looking at what task is urgent or requires your attention right away, right? So you're thinking that, okay, these are the tasks that you should focus on, right? Do you want me to do those tasks, right? So if you could say yes or no, right? If not, then you have to teach it, right? How you would do it, right? So it's actually, starting to get to this AI-led world, right? It's not fully AI-led because it doesn't actually suggest you what action to do, right? It just tells you these are the things that you should focus on, right? How do you do that? It doesn't actually quite know that yet, okay? But I will learn over time, eventually figure out how to do it and actually do some of those for you, okay? So now, this actually sounds a little scary, right, for a lot of you. So Anthropic CEO, Daria Amadei basically says that this is going to be a white-collar butt bath, okay? So scary stuff, right? So, but let me just give you a little bit of comfort by looking at, history and what happens, what would likely to happen, okay? So let's just use this cake delivery company under technology disruption as an example. Right? You see the parallel very easily, okay? 3 companies, right? They all have, like, say, 3 kind of these drivers who actually, or even cake deliverer, okay? There's no drivers back then yet, okay? Let's say it's a long time ago. So the productivity norm is like they get to deliver 10 deliveries per day per worker. So each one of these dots is essentially a unit of work that for one employee, right? So let's say we have some technology innovation, the automobile comes along, right? So this is the AI right, of today, right? Basically, automobile comes along. So now, basically, any single user, worker here can definitely deliver, 30 delivery a day, no problem with the car, right? You have a lot of excess capacity as well, right? So you don't need these other deliverer anymore, right? What do? A lot of people, a lot of business would just like let them go, right? Okay, but so what happens with company B, right? They say, okay, instead of getting looks like they have excess capacity here, right? Because I could also now I can use a truck that can actually carry more cakes and deliver more cakes, right? And then so I also could get rid of a couple of my workers, right? And then, not only that, I could also take on more business, okay? You could take on more and more business, and so does company A, they take on more and more business. But then, like, after a while, they find out, okay, this truck is actually, it's great, it can carry a lot, but, it's not fast enough, This car can only go to so many places in a day, right? So it can only get, like, this many units of work, like, this is 12 units of work done with one worker here, okay? So the limiting factor is time, right? So what if then company C actually comes along and says, well, what if I use a fast truck? I use a fast truck, right? So then it can actually get rid of these workers as well. Now it can actually use the full capacity of this truck, right? And then of course, company A is not going to sit around and do nothing. You say, well, what if I use a race car, right, to deliver, right? So the idea is that people are going to start to experiment and try to figure out how to optimize this technology, right? Nobody knows what's the limit of this yet, right? They're trying to figure out, right? Maybe the race car is not really suitable because, if you drive too fast, the cake get ruined. When you drive too fast and brake too fast, right? So that may not be a suitable technology, right? And then eventually, what you need is that, what you see that is happening right now today, right? Is this adoption phase, an experimentation phase, right? Adoption phase is where people stop hiring, right? You hear this news in the news already. Computer science graduates. Nowadays, no jobs, right? Painful, right? Painful, right? So hiring pause, job elimination, and then what the companies are trying to do, all they're trying to do is just trying to optimize the technology. How much can I get out of a worker plus this technology innovation? How much productivity can I get out of it? That's what they're trying to get, right? And then they do experimentation, right? What's the productivity norm, right? They basically, in every case, is always that people plus technology replacing people alone, right? People plus technology replacing people alone, right? So they're trying to experiment and see what is the productivity norm, right? Using this new technology, okay? And then after they figure out what's the maximum, right? They figure out, okay, maybe that, this race car is actually not such a good idea, right? Maybe a fast truck is the best you can do. Then there's some consolidation. Right? Consolidation going on. Basically, everybody is copying everybody else, right? Doing the same thing. Then here, tech consolidation happens when you have the establishment of best practice. So this is the best way to use this technology, okay? So best practices is created. And then, so now everybody have, this huge productivity gain. And then basically, you have a normalization phase, right? Now, the productivity norm is basically 160 units of work, right? So new productivity and new skill expectation. Any new kind of cake deliverer comes in are expected to know how to use a car, drive a car and deliver, and expected to make 160 units of work. That's the norm, okay? But then what happens? Then competition come into play, right? Competition come into play. Competition come into play means, company A is going to look and say, well, okay, what if I just hire one more person? If I hire one more person, then I could have double that 160 units of work, right? If they hire one more person, right, then what do you think company B is going to do? Company B is going to, of course, I'm going to hire another person too. Company C is going to hire another person, right? They're going to hire all those people back, right? Okay? So, and likewise, and company C says, well, what if I hire one more person? If I hire 3 people, right? Then, company A and B are not going to sit around, right? Competition is going to drive a lot of these, So this is when rehiring, right? Maybe not to the previous level, right? Maybe you don't need, you really, there's not enough demand for you to deliver 160 units of, work of cakes, right? That many, right? Because each one of those is 10 delivery, right? So 1,600 cake. You don't need that many cakes, right? So maybe these new workers are not to deliver cakes anymore, right? This worker may be there to, fuel and make sure this fleet is actually clean and upkeep and maintain the fleet, okay? So that's what's going to happen, okay? So you have this rehiring back. Competition is going to drive a lot of this rehiring and new job creation, okay? Okay, so that's how this is going to happen, right? Today, we are at this very, very scary phase right here, right? We're seeing all this uncertainty, but this has happened in history before, okay? Today, instead of automobile, is these AI agents today, okay? Many new jobs will be created, essentially, due to AI agents as well, okay? It could be, instead of one agent, it could be one person managing 3 agents, or it could be one person managing an agent who manages 3 other agents, right? So, but keep in mind, there's actually a natural limit to how many agents human can manage effectively, okay? Because these agents are also not free. They also cost money, right? So there's some balance that's required to maximize ROI, okay? So even though there might be a bloodbath, but the bloodbath is only transient, okay? But one thing I do want to remind you is that AI will not replace you. Someone using AI will. So what's the one best thing that you could do for yourself and your team? What's the best thing that you could do for yourself and your team? Yeah, essentially to cede control to AI, okay? Because if you keep on holding to what you do, right, then you're more likely to be replaced by those people who are using the AI, right? If you keep doing exactly what you want to do, you hold on to it so tightly, right? That means you're not going to let AI do any of your job, then someone using AI is going to be more likely to replace you. So the best thing you can do is learn how to relinquish some control, not all control, some control to this AI, all right? So thank you for your time. So come to our booth, and we'll show you some of the agents that we have and how we can help you drive revenue through those agents. All right, thank you. Yeah.